Welcome. I present the paper, The Curse of Dense Low-Dimensional Information Retrieval for Large Index Sizes. In this paper, I present issues with dense retrieval when the index sizes gets larger and larger to 100 million of documents. So for the beginning, some background. So for sparse representations for information retrieval, we represent each word in our language as an own dimension. So when we have like 100,000 words in our language, we have 100,000 dimensional vectors. And for every word in a text in a document, we set the value to a non-zero value. So most values will be 0 in our vector. In contrast, dense representations, we have some function f, which maps the text to a low-dimensional vector space. Usually we have between 100 and 1,000 dimensions, and most or all the dimensions are non-zero. In the paper, I look at the question, how do dense representations compare to sparse representation when the index sizes gets larger and larger to 100 million of documents? For the beginning, a small example. So here we evaluated the performance on the MS Marco passage retrieval dataset. We have a query from the Bing search engine, and we want to find the relevant passage which provides the answer to the query. If we select a small corpus, so we only have 10,000 documents in our corpus, and we compare BM25 with sparse lexical retrieval compared to a simple dense model, we see that the simple dense model is a lot better. So it's 9 points better MMR at 10 than the sparse model. When we go to 100,000 documents in our index, we see that the performance drops, or the performance difference drops between the sparse and the dense model. But still, the dense model is a lot better. If we go another magnitude to 1 million documents, we see that the difference starts to even decrease further. So here we have a difference of just 2 points, but still the dense model is better than the sparse BM25 model. If we use the full corpus of 8.8 million documents, we magically see that the sparse model BM25 is better than the dense model. So for small indexes, so if you only have like 10,000, 100,000 documents, the dense model here we tested here was a lot better than the lexical model, but for 8 million documents, it performed worse than the lexical model. And the question is now, what happens when we go even further to 100 million or 1 billion documents in our index? And note here, the dense model was a really simple model, a really simply trained model. There exist more better models which perform a lot better on these 8.8 million documents and also perform a lot better than BM25. But the question remains the same. What happens when we go from 9 million documents to 100 million documents or a billion documents? So in the paper, we prove a theory. In the theorem, we show that the probability for false positives. So false positive is you have some query and you retrieve some document which is not relevant to the query. It increases with the index size, which is quite obvious. If you have more documents in your index, the performance drops. What's more interesting is that the probability for false positives also increases when you have fewer dimensions in your representations. So when you go from 1,000 dimensions to 100 dimensions, the probability for false positives increases. You can check the proof in our paper. So far in the previous experiment on the MS Marco, we have the issue that the datasets are sparsely labeled. So we have a query, but only 1 or 2 passages out of the 8.8 million passages were annotated as relevant. But we cannot be sure if the drop in performance we saw, especially for the dense model, is due to the retrieval of unrelated, irrelevant passages, or just unlabeled passages. So it might be that the dense model retrieves some good passages which no annotator has seen and which the system considers as not relevant. To exclude this alternative theory, we did the following experiment. We took a small corpus where we only have the relevant passages, and we added a lot of noise. We added noise in the form of random strings. So we were generating random strings and we're adding it to the corpus. And then we checked for how many queries did the retrieval system retrieve such a noise string at the top of the top position at rank 1 of our output. We did it for different sizes. So here we added 100K documents, which are just noise, 1 million, 10 million, and 100 million documents, which just consist of random strings. And BM25, which is a sparse lexical model, does not retrieve any of these passages at the first position. If we look at the dense models, so we took one dense model with 128 dimensions for MS Marco, one model was 768 dimensions for MS Marco, and we took the DPR model from Kapukin et al. And evaluated on the NQ dataset. And we see with 100K documents for roughly 2.1 to 2.7 of the queries, such random document is at the first position. And this increases. So if you go to 100 million noise documents in your corpus, roughly every 10th query you ask, such a noise corpus, such a noise document is returned. And we can also see it in the vector space. Here, the red points are random documents. Blue points are queries, and green points are valid documents. And we see there's quite an overlap between the random documents, the queries, and the documents. So it's not surprising that we retrieve random irrelevant documents. So in conclusion, sparse retrieval has high precision, low recall. Dense retrieval, you can characterize it as low precision, but high recall. Dense retrieval works better on smaller corpora, and also dense retrieval is sensitive to noise in the index, so make sure to denoise your index before you apply dense retrieval. And if you use fewer dimensions for dense retrieval, you will get higher error rates. An important finding is that evaluation results cannot be extrapolated. So best system for 100,000 documents might not be the best system for 100 million documents.